I will explain how to get the solution for a single overhanging beam. A beam ABCD is hinged at A and it is having a roller support at point B. Actually, this is point B. It is having a hinge support at A, then having a roller support at point B. So for this beam, now we have to find the reactions, determine the support reactions. That is the question. So this diagram will be provided in the examination or in the question paper. This is called as loading diagram. This is called as loading diagram. So once the loading diagram is given, we have to draw the free body diagram of the beam. So below the loading diagram only you have to write the free body diagram. Now I will try to draw the free body diagram for this beam. So first write the beam as it is. The length of the beam should remain as it is. Then identify what is the type of support at A. Since it is an hinge support, it produces two reactions. Since it is an hinge support, it produces two reactions at point A. One in the vertical direction, I will call it as RA, and one in the horizontal direction, that is HA. One in the vertical direction, one in the horizontal direction. Since B is a roller support, it produces only one reaction, that is I will write RB. So this is the very important component of this chapter. First, finding out the reactions. So now totally this beam is having three reactions, that is RA, HA and RB. Only three reactions are there and I have three equilibrium equations, so it is a statically determinate structure. So I have three reactions. I have three reactions is equal to three equilibrium equation so it is a statically determinate structure. Then now I will convert all the loads present on the beam into a point load. For example, this beam is having a UDL. How I can identify this as a UDL? Because they look at the unit, it is 10 kilonewton per meter. This is UDL. And this beam is having an UVL, that is 30 kilonewton per meter is the unit. Then there is a point load of intensity 100 kilonewton, but it is in inclined direction. We can resolve it. So now I will write the loading diagram now. Now just to see, since this force is in inclined direction, 100 kilonewton, this force is in inclined direction, I will resolve it. We can resolve it into left component and downward component, as we know in the resolution part. The left component is 100 cos 45 because we know the angle with respect to the horizontal, and the vertical component is 100 sin 45. So this is acting at a distance of 1 meter from the left end, this point load I am speaking. Then we can convert this uniformly distributed load into a point load. I can convert this uniformly distributed load into a point load. How I can convert that one? This is 10 kilonewton per meter multiplied by, through the span it is acting, totally it is acting through the span of 3 meters. So into 3 meter, meter and meter will cancel, so the ending value will be 30 kilonewton. So this is the conversion of UDL into a point load. This is 30 kilonewton. This will act exactly at the center, 1.5 meter from left end, and from the right end also it is 1.5 meter because the overall span is 3 meter. Then I can convert this uniformly varying load into a point load. How I can do? Just by, because the area of the triangle is half into the base is 1 into 30 kilonewton per meter. Meter and meter will cancel. 30 divided by 2 is 15 kilonewton. Where this 15 kilonewton will act? We know that this acts at a distance of 2/3 of 1 meter from the this side, that is the least acting point, and 1/3 from the highest intensity point. 2/3 and 1/3 from the highest intensity point. So once we do this one, then we can apply the equilibrium conditions to get the solution. There are three equilibrium equations basically. One is summation fx is equal to 0. Second condition is summation fy is equal to 0. And the third condition is summation m is equal to 0. So I will use these conditions, three equations, and there are only three unknowns. I can get the solution. The first condition I will use summation fx is equal to 0. Now look at this diagram. This is called as free body diagram, FBD. What are all the forces acting in the free body diagram in the horizontal direction? One is HA, keep as it is. Then it is this force acting in the leftward direction, minus 100 cos 45 is equal to 0, because only there are two forces acting in the horizontal direction. Therefore, if you solve HA, you will get 70.71 kilonewton. 70.71 kilonewton. Call this as equation number 1. From the equation number 1, you have got the value for the first unknown. Then I will apply the second condition, summation fy is equal to 0. Now, what are all the forces acting in the horizontal direction in the loading diagram? If you see, one is Ra, then 100 sine 45, then it is 30, then it is 15, then it is Rb. So I will write this: upward forces are positive and downward forces are negative while calculating Fy. So it is Ra plus Rb minus 100 sine 45 minus 30 minus 15 is equal to 0. Call this as equation number 2. Call this as equation number 2. Then, looking at this beam, either I can select the moment point as A or B, because A is an in support and B is the roller support. I can either select point A or I can select point B to calculate the moment. But for my convenience, I will be selecting point A to calculate the moment. To calculate the moment, I will be selecting point A now. So I will take the third equilibrium condition. That is summation ma is equal to 0. Now please look at this loading diagram. Now this A as the moment center I have selected. Since moment can be created if we have force into perpendicular lever arm, since Ra and Ha is passing through A only, these two forces will not create movement at A. Then 100 cos 45, again it is passing through A, so this force is also not creating any movement at A. Then 100 sin 45 will create movement. A is the movement center, line of action of force is downwards, perpendicular lever arm is 1, so this will create moment. Then A is the moment center, line of action of force is downwards, and this force create moments, and the lever arm is 1.5. Then A is the moment center, the line of action of force is upwards, so this force creates moment. Then A is the moment center, line of action of force downwards, and this is having a perpendicular arm, and it will create a moment. So if I simplify and if I write the equation, this equation will be in the form of, that is, RA into 0, there is no perpendicular lever arm, plus HA into 0, there is no perpendicular lever arm, plus 100 cos 45 into 0, there is no perpendicular lever arm. So these three terms will be lending to 0 because there are no perpendicular lever arms. I hope you are getting this point. Then plus 100 sine 45 into 1 clockwise, plus 30 into 1.5 clockwise, plus 15 into the total distance from A to 15, this total distance. From here till this point it is 3 meter. Then this remaining distance is 1/3 of 1. 1/3 of 1 means it will be approximately 0.33 meters. And since it is 0.33, the lever arm will be 15 into 3.33 meters. Then minus this one. This will create an anti-clockwise. So it is minus RB into 3 is equal to 0. From this equation, if you further simplify, after simplification, you will get RB value as 55.22 kilonewton. That is the value of RB you will get from this equation, third equilibrium equation. Now use this value in equation number 2. Use this value in equation number 2 and you will get the value of RA, that is 60.49 kilonewton by using this condition. So this completes the problem. So this is the loading diagram. Below that you have to write the free body diagram, then apply the equilibrium conditions like this and you can get the solution. Thank you.